few things that are surprising about our kernel. The first one is one that I think I find the most surprising until you understand that we're based on a slab allocator, and there's a bunch of good things that come about as a result of this. But the key thing is that, unlike a Linux's kmalloc and kfree, you have to know the size of your object when you free it. So this means you have to keep track of bookkeeping if your sizes are variable. Now, it turns out it's a really good idea if you're to allocate things that are not variably sized. So most of your data structures, like a message block or a device state structure, those are fixed size. So guess what? You already know the size implicitly, so it makes it easy. So you just pass size of in the function arguments. Everything runs in a thread. It's been a while since I've spent much time in the Linux kernel, but certainly in other kernels that aren't threaded, this can be quite different. And it means that you do have to think about things like concurrency and reinstancy in ways that you might not have had to in other operating systems. Typically we don't, although we do have a way to have there's an enter critical and an exit critical, we do have a way to kind of block interrupts. Normally you don't want to do that. You want to use locks to ensure your concurrency is correct. The way our device tree and auto configuration works is quite a bit different too. And I'm going to talk quite a bit more about that, as well as some of the other things here. So we have the DMA interfaces work a little bit different. Solaris was designed from the get-go for big systems, Spark systems that have different architectural considerations than a typical PC. And so the interfaces are different and more complex. They're richer, but they come at a certain level of complexity. And I have some links to that. One of the cool things is a lot of drivers, you find yourself accessing device registers and dealing with endianness concerns. And you see a lot of if, def, big endian, little endian. Not in Solaris. You don't need to do that. Most of the time you don't need to do that. You can declare when well, I'll talk more about this, but there's interfaces that allow you to basically say, this space is big or little endian, and let the framework deal with the problems for you. So, and in some cases it does it better than you would do. For example, in Spark, you can have an address space that is endian, a mapping that is endian aware. And the other thing that tends to mess people up is when we run a 64-bit kernel, much of our user space are 32-bit processes, but not all of it. And so we have to deal with that complexity. For example, when you're copying data structures around, the size of a pointer isn't necessarily the same in user space as it is in kernel space. And so you have to be aware of that. Just a quick list of some frameworks. So the GLDV3 is actually stands for generic LAN driver. This is the interface you would use if you're writing a NIC driver. I should actually have links to man pages on here. I don't. Ask me or ask on the mailing list. SCSI and SCSI v3 in particular is for all SCSI devices, and also by association SATA devices, and a bunch of devices that use a different underlying transport but speak for reasons that I don't understand SCSI, like USB mass media. Actually, that ties right into BlockDev, which is a new one that I've created for simple block-oriented devices. So like a RAM disk or a flash device. If you don't speak SCSI, BlockDev is a nicer way to be. USB-A, USB architecture, right? So SCSI, by the way, stands for Sun Common SCSI Architecture. USB-A stands for USB architecture, right? Boomer was a framework for audio devices. I wrote the interfaces for Boomer, and sadly undocumented. That's stuff that needs to get fixed. I wrote all the man pages, but I don't think I can access them anymore. Or at least they may be published in PSARC, but I don't think we can republish them. I don't know what the rules are there. The Nexus framework would be, Nexus drivers are devices that are like bus devices typically. So they have children underneath them. So all SCSI HBAs, for example, are Nexus devices. They may also support a target functionality or a leaf device functionality. In Solaris, we call these Nexus. The idea is, if you're in a device tree, you have a node in the middle, it's a Nexus. The ones, if you're an endpoint with nothing else, you're a leaf. And it turns out that there's also some functionality that you could have that's leaf functionality on a Nexus. So you can have a driver that's a Nexus and a leaf driver together. And streams, I've already mentioned. Streams drivers and streams modules are a topic unto themselves. So about the device tree. All the devices on the system are presented in a tree. It's very simple, just like on a bus. So if you looked at like the Microsoft, if you're a Windows guy, right, or you pull down, you give the tree view, it's the same idea, conceptually. Solaris has been this way from ancient history, right? And it comes from the, there's a F code, the PROM standards, the IEEE 1275 standards, that specified how this was going to be represented. And we pushed that even in the x86 model. We present the x86 devices in a similar IEEE 1275 format, even though it, we get them from ACPI in a different, or actually there were even older enumeration methods. To look at the device tree, you can use PRTconf. And I like to use -VP, which allows me to see the PROM nodes. PROM nodes are basically devices that came from ACPI, BIOS, or F code if you're on a Spark. And of course, on a node, you can decorate a node with properties. And both the nodes and properties can come from hardware and software. So if I'm a USB device, right, for a camera, when I plug it in, it's going to get a node in the device tree. But the node actually, even though it's a hardware node, it actually gets created by software, and it won't show up in the hardware list, probably. However, if the node was passed in by PROM, it would be considered a hardware node normally. That's the big distinction. Let's see, any questions about the device tree? If folks have questions, or just stop me. So here's an example of a printout from PRTconf. This was actually run, you can see it was a joint SmartOS machine. You have the ACPI nodes, and this is not by any stretch of the imagination a complete thing. The thing would have scrolled and scrolled and scrolled. So I just took the first piece of it. And one of the key things here, as you can see, there on the bottom, so you've got, at the top, you've got this ACPI root complex node, right, which is kind of a virtual node. And then underneath it, you've got a node with some PCI compatible properties. So this was actually a real device. In this case, it's a host bridge, right? And you can see the properties underneath. What's the PCI properties like the maximum latency, the dev select speed, and class code, and all the stuff that you get from PCI configuration space, right? As well as the node name is down there, the node name is one of the defaults for how a driver determines its binding. The compatible property is the other one. And you'll see there's a list there, and we'll talk more about that. So actually this segues right in here. So going back, we have our compatible property, right? So when I have a driver name, I'll have a driver name for E1000G, for example. I can list how it's identified, how the system decides that this driver is for this physical piece of hardware. And it maps by this compatible property. So there's the standards for this. Actually, this goes back again to the IEEE 1275 standards that say these are the rules that you create for names. So PCI ones look like PCI, vendor ID, comma, device ID, and then there's extensions for functions and class codes and all that. They're listed, and the order that it will bind, it'll choose the first one of these things that matches. And you'll notice the first one that's listed in the compatible property is a very lengthy, very specific binding, and then it becomes gradually less and less specific until you're all the way in just anything that matches PCI class, which is a sort of all host bridges in this case, right? And the way we the way we associate this is, and I didn't put this in here, I should have. There's a file called etc driver underscore aliases, and that actually contains the actual bindings that are registered on the system. You shouldn't edit that file directly, but it is useful sometimes to go look and see, I see this PCI node, what, do I think it's going to be supported? Go look in the etc driver aliases, right? I talked about the it's actually not it's compatible, so that was an error. This PCI node, 8086,1000, that's actually an E1000G device, so that would be a real example. The other thing is that once I establish this binding, if I bind PCI 8086,1000 to a driver, say E1000G, no other driver can be associated with any other instances with that match that, right? I'm gonna match that binding, and there's ways to kind of do some things, because remember we had that sort order, so you could have one driver that's associated with a very specific one, and a different driver that's associated with a less specific one. If you find yourself doing that, you're probably doing something wrong. I haven't seen that normally used. Let's see. There are some special, okay, so the other thing is we don't probe, unlike Linux or NetBSD, I don't know if Linux still does this, but like NetBSD does this, where you, instead of having the system know what hardware matches to a device, this is essentially external metadata in the form of these alias bindings. For NetBSD, you would have instead like a probe function or a match function that says, does this device match this attribute? So it's code in the driver. Generally, we don't see that in Solaris. We have what are called self-identifying devices like PCI, USB. They all identify themselves by this nice alias. Does anybody remember the old ISA devices where you had to wire in IRQ and address, which IO address is it on and all that, right? So that would be the exception. And then you could still implement device drivers that do this, and they have a probe function, and it's evil. And so that is the old way. Those would be for non-self-identifying devices, and we do have some of that. Actually, ISA fortunately did go have this plug-and-play framework to be smarter here. So with PNP ISA, it's self-identifying. When a Nexus driver creates a target, creates a child, it can supply a node name, and the node name is always implicitly an alias. So for a software device, like the SCSI framework will create maybe the SCSI framework is a bad choice. The BlockDev framework will create a child of a parent device with a name BlockDev, and that is automatically an alias. So the other thing in the device tree is we have minor nodes. So minor nodes are service points. This is how you get at a device from user space normally. Basically, they're character special devices. A Nexus driver doesn't need to have a character special device. You're not going to read and write from an HBA normally, right? You read and write from a disk, as an example. Or you're not going to read and write from a PCI, host bus adapter, pardon me, rooted, like a host adapter. That's not the right terminology, but anyway. However, you could implement that functionality if you wanted to, and some of the HBAs or some of the Nexus drivers do provide that functionality. With a minor node, what happens is that the access point is really a character special device. The character special device is created automatically on behalf of the driver when the driver does the in-kernel work to say DDI create minor node. So if I call DDI create minor node, I'm going to automatically get a node created up in the device's file system. Okay, now that's step one. Step two is, if let's say that was a disk node, I want a node out in dev DSK. Well, based on the type of node I created, dev FSADM will then create a symbolic link to it in the devices tree, in the /dev tree, which is where, if you're a Solaris or a Illumos person, you expect to see these kinds of devices. And you can actually create your own plugins to dev FSADM to customize how your nodes get presented out in the dev tree.